All right, this is Honors Algebra 2 Pre-Calculus. We're doing section 9.4 in Pre-Calc. On page 651, we're going to talk about finite differences. So in 9.2, we saw that arithmetic sequences had an nth term that was linear. So for instance, a sub n equaled a sub 1 plus the quantity n minus 1 times d, which in the example of the arithmetic sequence 3, 8, 13, 18, a sub n would be 3, that's a sub 1, plus n minus 1 times the common difference, which in this case is 5, because you can see I'm adding 5 each time. So if I clean that up, I would end up getting that a sub n is 5n minus 2, right, which is linear, like mx plus b. This sequence has constant first differences, d, which is why it's arithmetic. So what I mean by first differences is if I find the difference between 3 and 8, I get that it's a plus 5, right? And from 8 to 13, I find that it's a 5, and from 13 to 18, I find that it's a 5. We call this whole row of things the first differences. So what I'm going to do in a second is show you an example of how we can calculate second differences. And you can find third differences and fourth differences, but we're going to go ahead and talk about second differences first. So let's talk about second differences. So let's look at a different sequence. Let's look at the sequence, I'm going to be kind of lazy. I'm going to go with 1, 4, 9. I'm guessing you can see the pattern. These are just squared numbers, right? Cool. All right, dot, dot, dot. Okay, so I just picked the laziest version of this sequence that I could. So let's look at the first differences. The first differences of this sequence, right, so the first differences are not constant, all right? So the first differences, which is what we'd normally look for to see if something is arithmetic, they're not constant. To get from 1 to 4, I'm adding 3. To get from 4 to 9, I'm adding 5. To get from 9 to 16, I'm adding 7. And then to get from 16 to 25, I'm adding 9. And to get from 25 to 36, I'm adding 11. They are not constant. But those first differences themselves do actually make their own arithmetic sequence. The second differences in this situation are constant. So what we mean by second differences is the differences between the differences. So the difference between plus 3 and plus 5 is a plus 2. The difference between plus 5 and plus 7 is a plus 2. The difference between plus 7 and plus 9 is a plus 2, and so on forever, right? Okay, so what I want you to notice is the second differences are constant. Okay, so what that means, so see how the second differences are constant. So we saw that when the first differences were constant, we had a sequence that was arithmetic, and that the a sub nth term was linear. Well, now what this means is that my a sub nth term is a quadratic. Okay, so because those second differences are constant, my a sub nth term is something quadratic, meaning it's going to have a squared, which is a helpful thing if you're trying to spot the pattern. Now, as I mentioned, in this particular instance, I picked a really boring version of this sequence. I picked the version where it's literally just n squared, right? You can see by inspection that if I made my a sub nth term n squared, when n is 1, I'd get 1 squared. When n is 2, I get 2 squared, 3 squared, 4 squared, 5 squared, etc. And that's my term, right? But I can give you a harder version of that, and that's what we're going to do in example 7. In example 7, because sometimes I lose count, but I'm pretty sure we're on 7, I'm going to walk you through finding a quadratic model for a different group of these. Okay, so that's kind of the gist. So let's walk through example 7. All right, so in example 7, we're going to go with, we'll actually use the one that's on page 651 because I'm going to be lazy. So we're going to go with 3, 5, 8, 12, 17, 23, dot, dot, dot. Okay, so let's find our first differences first. So the first differences are not going to be constant, right? So my first difference is going to be plus 2, plus 3, plus 4, plus 5, plus 6. Okay, my second differences, though, are constant because the difference between a 2 and a 3 would be plus 1, and the difference between the plus 3 and the plus 4 would be a plus 1, and so on. Okay, so what this tells me, right, this tells me that I have a quadratic formula. Okay, so I don't know much about it, but I know that whatever my nth term is, it's quadratic. So what I mean by that is that a sub n must be some, and I hate that the book used a, but they did, so we're going to stand by it, a n to the second plus b n to the first plus c, right? Like ax squared plus bx plus c, but we used n's here instead. Now, the way that the book suggests that you figure out this formula, which is clever and totally fine, is that you're going to go ahead and try some n values. So if n was 1, you know what value you get when n is 1. When n is 1, you get the first value, right? So a sub 1 is a 3, which means that's a times 1 squared plus b times 1 plus c. So you now have an equation that 3 equals a plus b plus c, right? If you try n is 2, right, that's the a sub 2 term, right, which you can see is 5. Well, that's going to be what happens if you do a times 2 squared plus b times 2 plus c, right, which is going to be 5 equals 4a squared, sorry, not squared, 4a, my bad, plus 2b plus c, right? And if you did n is 3, right, the third term is an 8, so a sub 3 was an 8, which would be a times 3 squared plus b times 3 plus c, so you're going to get 8 equals 9a plus 3b plus c. So what's going to end up happening is you have 3 equations. Now, if you recall back to Chapter 4 in Algebra 2, which is also Chapter 7 in this textbook, the easiest way to solve this is to use matrices. So I have 3 equations and I have 3 variables. That's the minimum number of unique equations I would need to solve this. So I'm going to write my 3 equations over here so that I don't have to reinvent the wheel. So I'm going to go ahead and put my constants on the other side because I prefer to have my variables on my left-hand side. So my 3 equations are a plus b plus c equals 3. 4a plus 2b plus c equals 5. 9a plus 3b plus c equals 8. Now, I'm going to walk you through a couple different ways to solve this system to find what a, b, and c are to write this term. But I'm going to point out that if I had a calculator on this question, I would 100% use my calculator. So I will walk you through a couple options. Remember that our end game here is to write some nth term. A sub n is a n squared plus b n plus c, right? That's going to be my end game, is to find the values for a, b, and c. But let's walk through some options for how to do that. So legit, I would definitely totally lean on my calculator if I had a calculator here. So if it's me and I have a calculator, here's what I'm going to do. Okay, so I'm trying to solve for a, b, and c, and I really don't care how you get there. You can use substitution, elimination, and a whole bunch of different combinations. You could use Gaussian elimination with matrices if you want. But if I have a calculator, here's what I'm going to do. I'm going to enter my matrix A in my calculator as my coefficient matrix, which is 1, 1, 1, 4, 2, 1, 9, 3, 1, right? I have so that's going to be my matrix A in my calculator, right? I have this variable matrix, A, B, C, that I don't put in my calculator, right? That's like that X that we don't put in. And I'm going to set that equal to my constant matrix, which is the 3, 5, and the 8, and I'm going to call that matrix B. To solve for my matrix ABC, the easiest way to do it is to type in my calculator the A matrix inverse times the B matrix. And that's going to do it for me really, really fast, which is super awesome. So to put that in my calculator, right, I'm going to go, so I want to go to matrix, right? And matrix is right above the X inverse button. So you hit second X inverse, and it's going to take you matrix. You're going to go over to edit, and for matrix A, you want it to be a 3 by 3. 1, 1, 1, 4, 2, 1, 9, 3, 1, right? And you're going to double check that that's right, and it wasn't because I made it an 11. So you're going to double check that that's all right. And then you're going to quit out, second mode. You're going to go back to matrix. You're going to go over to edit, and you're going to pick matrix B, and you want matrix B to be 3 rows by 1 column, right, which looks like this, and you want it to be a 3, a 5, and an 8, right? And then you're going to check that it's right and quit out. Now you're going to go back to matrix. You want A inverse, right? And then you go back to matrix and you pick B. And that should give you the values you need. And that's a lot faster than any other option you're going to come up with. So what ends up happening from that is that I get that A, B, C is 0.5, 0.5, 2. So my answer is that A sub n is 0.5 times n squared plus 0.5 times n plus a 2. And that's not something you were going to come up with easily on your own. So that's my explicit term for the nth term of this sequence. Now that's fine. I did point out that there are a few other options to get there. The other option that would work really well is if you used elimination, you could knock out this C pretty easily from either of these equations, right? So one easy way to do this, and it's up to you, you don't have to do it, but I'm going to walk you through a different option just in case you wanted to see one. The other way I might do this is I might do it with elimination. So I'm going to number my equations 1, 2, and 3, and you're not going to be expected to do this on a test with me or anything else. I'm just walking you through how you could figure this out if you wanted to. We did this kind of stuff when you did a chapter that involved solving these systems, and you don't have to do it right now, but I just want to walk you through. So One option is I could take both equations 2 and 3, which are the slightly uglier equations, and subtract equation 1. So I could take equation 3, which is 9a plus 3b plus c equals 8, right? And I could literally subtract equation 1, meaning I'm going to subtract a plus b plus c equals 3, right? And if I did that, I'd get this new equation that was 8a plus 2b equals 5. Great. I could do the same trick with equation 2, which was a 4a plus 2b plus c equals 5. And I could subtract equation 1, which would be subtracting a plus b plus c equals 3. If I did that, again, the c would magically disappear, and I'd get 3a plus a b equals 2. Well, now I have this equation, and I can solve them pretty easily by elimination. So I would probably then say, cool, I'm going to multiply this whole thing by a negative 2, right? And I'm going to get 8a plus 2b equals 5, which was this equation up here. And a negative 6a minus a 2b equals a negative 4. Well, when I add straight down, I'm going to get 2a equals 1. And then it doesn't take a whole lot of work to recognize that a is a 1/2, which is what I was supposed to get. Once I know a, I can use either of these to back substitute and get b. So 3a, which was 3 times a half, plus b is a 2. That's 3 halves equals, 3 halves plus b, rather, is a 2. So b seems to be a positive 1/2, right? Because this is 4 halves minus 3 halves. So b is also a half. Check. Once I know a and b, it's a really simple matter to plug in and find c. I'd probably plug into a plus b plus c equals 3. So once I know that, right, now that I know a is 1/2, right, I know a plus b plus c is apparently a 3, and I now know that a is a half plus b, which is a half, plus c is a 3, so that's 1 plus c is a 3, and I get c is a 2. So again, I end up with my a sub nth term as a 1/2 n squared plus a 1/2 n plus a 2, which is the same thing we got when we used the calculator. Again, it's up to you. So what's cool about this is that if you can recognize that a sequence has these second differences that are constant, it's easy to spot and say, oh, hey, I get that that's quadratic, and then you can start from knowing that the formula has to look like this, and you can kind of figure out what the formula is. Most of the time, they're not as ugly as they are here in example 7. Most of the time, they look an awful lot more like that 1, 4, 9, 16, 25 that I gave you earlier.